So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be going over how you can train your own word vectors with Facebook's fastText library. Let's get started. Now first of all, what are word vectors? Now, word vectors are related to the field of natural language understanding and natural language processing. In essence, they enable you to represent words in a mathematical vector space. So you can actually quite literally represent the semantics of different words instead of the syntactics using, well, mathematics, enabling you to take abstract concepts like, of course, natural language and what we mean by it, and represent it in a fixed dimensional vector space. Now, I know it sounds very confusing, but let's go ahead and take a look at an example of word vectors in action. Now, first of all, how would you traditionally do natural language processing? Let's just say that word vectors don't exist. So let's go ahead and take a look at an example. Now, let's just say we wanted to build a spam classification system. How would we do it? Well, you might take a few different messages, all right? And you might take a look at all the different words there are in those messages. And then you create a unique list of all those different words. So basically every single possible token in those words. And if, well, you have a token that's not in that set, then you consider it out of vocabulary, OOV. Now, in order to represent this data for a neural network, of course, you can't feed in characters. So you would need to one-hot encode your entire vocabulary. So let's just say you're working with spam and you've got, say, 20,000 words. Okay, so you've got 20,000 words. Now, let's just say we're working with a regular old dense neural network here, a multi-layer perceptron. We're not working with any of the fancy long short-term memory neural networks or anything of that sort. Now, let's just say in the input, and of course this is not going to work very well, but let's just say you had a neural network similar to this one, where you have 20,000 inputs, and your very next layer has even, say, 700, or even just 700 neurons, all right? 700 units. Now, if you were to take a look at the amount of connections between 20,000 and 700, that's not very scalable. That is not going to work well because you've got way too many weights just between the input and your first layer. You're not going to be learning anything nearly useful, and it's going to take a very, very long time to train. You're going to need intense regularization techniques, there's intense chances of overfitting, and overall, it's not a very good technique. So you need another way to represent your input. And, of course, instead of representing it syntactically, like you are now, individual words, you somehow want to represent it semantically as to what the words actually mean instead of, well, which words they are. Let's take a look at how you can do that. Now, of course, we're going to be using neural networks. So let's take a look at the word vector technique. The word vector technique essentially enables neural networks to understand what certain words mean by understanding what words come before and after it. As John Rupert Firth said, for example, he's a very, very famous linguist from a few decades ago. He said, you can understand a word by the company that it keeps. Now, we're going to be doing something similar to what he entailed, but this time with machine learning. So let's take a look at a simple sentence. So let's just say, Tanmay Bakshi is recording a YouTube video. Actually, let's continue the sentence. For his channel. All right. Now, when you take a look at this sentence, how can you understand what all the words in this mean? Now, let's just say we were to take a look at a simple task. Say next word prediction or context prediction. Now, let's just say we take a look at the word Bakshi. Can we train a neural network to predict the word that came before it and the words that would come after it? That's what the word-to-vec technique entails. But I know what you're thinking. Well, how would that be anywhere near accurate? You could have tons of things before and after words. Well, the interesting thing is, due to the way that neural networks learn, we're not interested in the final output at all. We're interested in the way that the neural network got to that decision. Let me tell you what I'm talking about. So let's just say you have a 20,000 vocabulary size, all right? So you've got 20,000 words in your data set. Now let's just say you fed them into a neural network where the next layer was 300 units long. That outputs back into a 20,000 long unit neuron. Now, this sounds pretty interesting, doesn't it? How we have a neural network that inputs 20,000, outputs 20,000. Might look like an autoencoder at first, but it's not. We're going to have different inputs and different outputs. Now, this is the way it's going to work, all right? We're going to define something called a context window, which is how much before and after a certain word the neural network should look for to make its predictions. Now, how big or small this is totally depends on your domain. If you're doing something like, for example, item recommendation, you might want to have a really big context window size because then you're actually understanding the patterns between a word and a ton of the things that come before and after it. If you're doing English, you might just have a context window size of 2 because if there's something occurring over here, it's not related to backsheet. You don't want to have that big of a window size. But if there's something over here, backsheet and recording are related because I'm recording a YouTube video. So it's important to have the right context window size, or your neural network, therefore your word vectors, won't really learn anything interesting. Let's go ahead though. Let's just say our context window size is 2, all right? And again, our word here is backsheet. Now let's go back 2 words. Of course, there are no 2 words, it's just 1 word. So we take a look at Tanmay, and we highlight that. Now let's look ahead 2 words. What are the 2 words? There's is and there's recording, all right? We highlight those words. Now there are 2 ways we can go forward. Either we can create 3 training examples where backsheet is the input, Tanmay is the output, then backsheet is the input and is the output. And then backsheet is the input and then recording is the output, all right? So for one of the same inputs, the output layer will have to fit, it'll have to fit to 3 different outputs, which of course will never give us high accuracy, but again, we don't care about this last layer because when we're done training the neural network, we're going to erase this all together. We're going to feed in every single one of the possible inputs, and after that, we're going to get the encodings for every single one of those inputs that the neural network learned. But still, let's get back to that in just a moment. Now, that's one of the options. You could have backsheet Tanmay, backsheet is, backsheet recording. Or what you could do is you could say Tanmay backsheet is backsheet, recording backsheet. So you could flip it around. If you do backsheet and then Tanmay, that's called the skipgram model. Now these are usually known to work better, but if you were to do the other way around, where you take the context and predict the word that it's coming from, that's called a continuous bag of words model, which is also good, but it's not nearly as good as skipgram. However, the fastText API allows you to actually use practically any kind of model you want. You can adjust all your parameters yourself if you like to. I would recommend skipgram for the majority of the things you would want to do when it comes to natural language processing. Now, similarly, you're going to go ahead and loop through the whole sentence. And every time you're going to look 2 words back and 2 words to the front. You're going to add all of that to your training data, depending on skipgram or continuous bag of words or CBOW. And then you're going to train your neural network on those examples. Now again, you train your neural network, you'll get a low loss, but your accuracy will not be great. Don't worry though. Why? Because the final classification layer where you've got softmax, you're going to be erasing that altogether. Then what you're going to do is one by one, you'll take your one-hot encoded inputs and you're going to run through them and collect a NumPy array of shape 20,000, or just for the sake of clarity, let's just make it 20,300. So basically you're going to have 20,000 arrays of 300 length each. Now these 300 will represent the actual encoding that the neural network gave you. Now the interesting part. With this neural network, you can, or with the encodings that the neural network provides, you can actually interpolate between different words arithmetically. So you can actually, with arithmetic, do operations on certain words. So for example, let's just say you have the word king. All right? Now let's just say you wanted to find out king in relation to another word, some sort of analogy. Let's just say you were to take the vector for king that this neural network outputs, the 300 length vector, and if you were to negate the vector of the word man, and then add in the vector of the word woman, what would the output be? As a human, you can intuitively tell that this should be equal to queen, of course. That's what makes most sense here. But this can now be done with a computer, because you're not understanding these words syntactically, you're understanding them semantically, by understanding the contexts in which they're mentioned with other words through a neural network. Now, of course, I do know that just a little while ago, I told you that if you were to have a neural network where you have 20,000 inputs and then 300 hidden nodes, you're going to be prone to overfitting. But in this case, it really doesn't matter as much as you might think, because again, all we're doing is we're getting the final encodings, or the embeddings, that the neural network provides, and we don't really care about whether it overfits on certain categories or not. And so that is exactly what I'm going to be showing you how to do today. Of course, there are some limitations to word vectors. Like, for example, let's just say that there's a certain word that's not in the vocabulary but still makes sense to humans. Of course, you could take any word and prepend UN or append towards the end ly, and you would eventually come up with a word that makes sense to humans intuitively. But the thing is, of course, the computer wouldn't, because it's not in this 20,000 list. There's nothing to feed into the neural network to get that 300 output. And so, the fastText library doesn't exactly use this algorithm. This is the original word-to-vec algorithm. fastText uses a modified version, and it is very, very fast. And I mean, it can train word vectors in seconds instead of hours. And so, what they do is this really interesting n-gram technique. So, for example, let's just say you were to feed in the word, let's go towards the bottom here. Let's just say you were to feed in the word matrix. All right. It's actually going to take a look at the word matrix like this. M-A, M-A-T, A-T, A-T-R, T-R, T-R-I, R-I, R-I-X, I-X, all right? It's going to sort of go through this using an n-gram technique. And then it's going to feed all of these into its own little system where it's going to calculate these word vectors. So if you have something that's not necessarily in the vocabulary but still makes intuitive sense, you should be able to come up with a word vector for that word. And so that's why the fastText library is so intriguing. Again, developed by Facebook Research. Now let's take a look at how you can go ahead and implement your own word vectors. And I'm actually going to be using an interesting data set. It's provided by Stanford, and it's actually supposed to be used for neural machine translation. It contains approximately 4.5 million sentence pairs, English-German, but we're going to be ignoring the German one for now because we only need English word vectors. From there are over 120 million individual words in this corpus. Let's go ahead and find out how we can train word vectors using this technique. Alright, so welcome back to the code part. Now let's take a look at how you can actually implement word vectors with fastText. Now remember, the whole reason that this is called fastText is because, well, it lets you train word vectors without needing to worry about spending time on, well, your word vectors. So instead of, for example, creating an embedding layer in Keras and then having to train that with the rest of your neural network, you can take these pre-trained embeddings from fastText and implement them in your Keras model, or any other machine learning model for that matter. Or even process your data beforehand and then feed it directly into your model. Now, in this directory, I've got 3 different files. These 2 are a pre-trained model that I've actually gone ahead and trained myself, and this is the data that we're using to train. So if I go ahead and take a look at the data here, open it up with Vim, as you can tell, the data is, well, there's a lot of it. If I were to, in fact, go ahead and show you the word count or the line count here, it tells me that there are 4,468,840 lines, and therefore sentences, in this document. Now, if I were to go ahead and show you, for example, the head of this document, this is just a few of the samples of what's in the document. Now, of course, this is meant for neural machine translation, so there's a lot of pre-processing in here. So, for example, there's a space before spam here and after the bracket. And so if I were to go ahead and make that a bit bigger for you, you can tell that there's a lot of formatting, but fastText should automatically take care of all the pre-processing that's required. Now, in order to train your word vectors, there's just one very simple command you need to run. fastText skipgram to train a skipgram model, pass it the input, which is, of course, your file with all your words, and then output to whichever model you want. Now, I've already trained this one, so let's output to model number 2. And it's going to start off by reading all the millions of words in your document. Now, the specific one that I fed in, there will be a link to this document in the description, has approximately 120 million words. But still, though, fastText is capable of training word vectors on this data in under 10 minutes easily, whereas lots of other techniques would take an hour or so to complete. As you can see, it gives you detailed statistics, including the learning rate of the neural network at the time, how many words are being processed every second on every thread, and so there should be like 8 threads running on this MacBook Pro, and therefore we're getting around 70,000 per thread, but it's slowly going up until it reaches sort of plateaus. It also shows us the loss value. Remember, the less here, the better. Over time, this is going to go down or up slower because the learning rate is decreasing linearly. It also gives you an estimated time of arrival, so currently it's around 10 minutes, and it also gives you a progress. Of course, you can control how many epochs it actually completes in the settings as well, but by default, even, the fastText models do give you very good accuracy. So let's go ahead, take a quick break, and let's see in the next 10 minutes if we get good word vectors from fastText. Alright, so we're almost done training here, and 99.9% and 100%. There we go. So as you can see, at the end, the learning rate was exactly 0, so it of course goes down linearly from 0.04 to 0. Those words per second per thread through the whole training session was 84,241, and the final loss value was 0.7633. Now it's going to go ahead and save the weights. Of course, the total number of words that were actually finally, that the neural network was trained on was 185,385. But now we're ready to go ahead and actually use our word vectors. So let's go ahead and run the following command. I'll tell you what it does in just a moment. Now, the following command is going to do this. It's going to run NN, which is a specific function of fastText. It's called the nearest neighbors function. And I'm going to pass it the model that we just trained, ende model2.bin. Now, it actually saves 2 files, the .vec file and the .bin file. However, the .bin file is what fastText generally uses, and the .vec file is what you're probably going to use in your applications. If I run this, it'll actually go ahead and initialize the nearest neighbor interface. The nearest neighbor tool allows us to see which words are closest to another word in the whole vector space. So let's go ahead and try it out. Say, for example, I type the word king. What's closest to the word king? It's the word queen, then throne, king, kings, thrones, dethrone, prince, duke, kingdom, and emperor. As you can see, the neural network has picked up a very good semantic representation of the words and what they truly mean. Similarly, of course, if I were to type in queen, it would tell me that king is the most related word in this sense. Of course, I can go ahead and actually take a look at other words. In fact, if I wanted to, I could go ahead and actually do some word analogies. So now I'm going to pause really quickly, open up a new Python script, and show you how you can actually calculate word analogies. Alright, so now this code that you see on screen right now will allow us to figure out the analogies between different words. Let's take a look. Now, this code over here essentially starts off by importing NumPy, CSV, sys or system, and cosine from CIPY spatial distance. Essentially, this will enable us to figure out the cosine distance between two different vectors. I start off by importing the vec file that I was talking about. Of course, the delimiter in this case is a space, since it's not a CSV file, but we are still using the CSV library in order to read the file. I convert that to a list from a generator, and then I do a quick list comprehension, and basically what this is going to do is it will remove the first element of the whole array, and from every sub-element it'll remove the last element. And so if I were to go ahead and show you over here, if I were to open up the vector file, as you can tell, the very first line is essentially how many words there are and the dimension of the word vectors. And then you've got, in every line, the word and then a space and then 100 numbers each delimited with spaces. If I were to go to the end of this, there is one extra space at the end, and therefore Python says that there's an extra value at the end, even though there technically isn't, or practically isn't, technically there is. And so basically we need to remove this extra space, and we have to remove this, which is what the list comprehension is going to do for us. After that, there are just two more list comprehensions. First of all, I create an array of all of the words, so basically the first element of every row, and then I create the actual vectors, which is the second element onwards converted to floats. And then I just go ahead and put those into a dictionary, so every key is a word and the values are integer or float arrays that describe the vectors themselves. Now after that, I create three different NumPy arrays, A, B, and C. So basically, I take the word vector for the first parameter that you fed into the Python script, and the second parameter, and the third parameter, and then I take those word vectors and I convert them to NumPy arrays. So to give you an idea of what that means, if I were to call Python analogies.py with king, man, queen, or king, man, woman, what it would do is it would set A to the value of king's vector, B to the value of man's vector, and then C to the value of woman's vector. But let's go back to the script for just a moment. So after that, I go ahead and create the actual final vector, which is the calculation, so A minus B plus C is the analogy vector, and then I go ahead and put a little bit of logic in to figure out which vector is the closest in the data set. And so I just create the closest word, closest score, and then I loop through the word vectors. I calculate a distance, and if the distance is less than the current closest score, and if that word is not any of the things that you typed in, then go ahead and set this current distance to the closest one, and set the current word to the closest word, and then go ahead and print out that closest word. It's essentially a very, very simple script. It's not necessarily optimal in any way. There are definitely better ways, more efficient ways you can implement this, but that's how this one works for now. So I'm going to go ahead and run this quick script, and if it works, we know we've created true semantic representations of natural language. Give it just a moment, and if it says final word queen, we're good to go. It's going to take king, negate the man representation, add woman, and any moment now. Almost there? Again, there are much more. There we go. It says final word queen, and just like that proves that we've got true semantic vector representations of natural language. Now, of course, there are many other ways we could do this. There are tons of other libraries out there. There are pre-trained word vectors out there. But for a lot of use cases, it's good to get your own word vectors. And for some use cases, like for example, product recommendation, your own word vectors are absolutely priceless. Alright, so that was a quick tutorial on how you can use Facebook fastText to train your own word vectors on your own domain or your own language. I really do hope you enjoyed that tutorial. Thank you very much everyone for joining in today. That's what I had for this tutorial. If you'd like to find out more, please do take a look at the code down in the description below. And apart from that, if you do have any more comments, suggestions, or feedback, feel free to leave them down in the comments section below. Apart from that, if you do believe this tutorial could help anyone else you know, like your family or friends, feel free to share the video as it does help out, and also feel free to leave a like down below if you did like the video. Apart from that, if you really do enjoy my content and you want to see more of it, feel free to subscribe to the channel as it really does help out a lot, and apart from that, turn on notifications if you'd like to be notified whenever I release new content. So thank you very much for joining in today. That's what I had for Facebook, fastText, and word vectors. Goodbye.